Okay, cool. So my project is DarkChess. Basically, DarkChess is a variant of chess in which players only see their own pieces and the pieces that they can and the places that they can legally move to. So basically, all the pawns can move either one step forward or two steps forward, and that is why the first these two rows are um, visible, while everything behind that is basically hidden. So the problem definition is basically how do you allow two people play a game of dark chess without a trusted third party? And I chose this because of I saw it on the Mina and FHE.org Discord. That's like Sama. And no one had proposed a solution to it under the threads. So it made it attractive because of that, something that I could solve. And it looked interesting and quite difficult, which is like the perfect mix, basically. So what makes it hard? Um, Only I know where my pieces are. So a certain player knows where their pieces are, and that information is private to just them. And then your opponent also knows where their pieces are, and that information is also private to just them. But then if your opponent's piece is on a square that one of your pieces can legally move to, then you should be able to see that piece. And then this is like the crux of the difficulty because of the piece locations are private to both players, but then you're still supposed to be able to know where the piece is if you can move there. And essentially, this is like joint competition on both parties' private inputs. So you start thinking about things like NPC, multi-party competition. But then trusted third parties, so like chess.com has this variant online, and they can do this easily because of they hold the private inputs for both players. So they know where both players' pieces are, and so they can perform this computation. So then you have to trust them to not leak that information in one way or the other. And basically, they are a trusted party. And the question is, can you do this without trusting them? So let's define the joint computation properly. So I have a set of squares where my pieces are and where they can go. So basically, I know where all my pieces are, and I know the squares that it can go to. So this is information that I have. My opponent has a set of squares that their pieces are located. And the goal is to figure out where these two sets intersect. So basically, where can I go that you have a piece on? That is the computation that we're trying to perform. So this is an example of this computation. So I have a rook, and the rook can move here, here, and everywhere here. So you also have your own sets of pieces location. So that's your nines and your pawn. So when I intersect the squares that my rook can go to, and the locations of your pieces, then I'm going to get a new piece, or the piece that I should essentially be able to capture, which means that I should be able to see this piece. So how do you do this privately without leaking, let's say, the knight, for example? And this is where privacy intersection comes in. So this is a cryptographic protocol that has existed for a long time now and is continually being improved. It basically allows two parties with private sets to compute the intersection between their sets without revealing any extra information or private information, if you will. So there are multiple ways to do this. But I decided to do it based on key agreements like the Feynman. Because of the set size is small, it's just 64. And I don't need any of the more complex methods to achieve this. So it's essentially the Feynman. Basically, if you have the same values for G, and then once you raise it to a private key and the second person's private key, it is order independent. So you're going to have the same shared key. And once you have the same shared key, then you know that there's an intersection at G. And you don't know any other thing if G is not, you don't leak any information if G is not the same, essentially. So with this, we can now get a version 1 of the DarkChess protocol. So let's say a player makes a move, then both players need to perform a refresh of their state based on that move. So A sends the encrypted location of his pieces to B, So basically, these are where all my pieces are. I am sending it to you. Then B does the same and sends it to A. So A computes the intersection between where B's pieces are and the squares that he can move to. And then B does the same. Now, this is a joint computation in the sense that this intersection check is an interactive protocol. So it's not non-interactive. It's going to be important later on. So essentially, at the end of this, both A and B would know the pieces of the opponent that they can capture based on what we showed in the here. So the problem with this is that it leaks more information than we need to. That's the problem with this current protocol. And I'll give an example here. So right now, two pieces are on the same line. So technically, the rook can go to all the squares and all the squares. But then what we really want is the rook should stop once it sees a pawn, and it shouldn't go further. But then there is no way to know this right now because of white doesn't know that there are pieces here. So white just sends the list of all the squares, and black just sends the list of all the pieces, and then they perform the intersection. So how do we solve this, essentially? So to solve this, we perform the intersection in a step-by-step process. So we first of all check for an intersection on the closest squares to the rook. So basically just the squares. And then we continue this. So we check for the intersection here, and then we check for the intersection here. So basically, if you look at it, it's just like move one step in all directions, move two steps in all directions, move three steps in all directions. So now there's no square here. So that's why we're not checking for anything again. And then move 4 steps. So now we have encountered a piece on this square. And then in the next iteration, we essentially don't check here anymore because of we have already seen a piece. So that piece is going to serve as a blockade, and then you should not proceed further. And then we finally check this square. So we do this 8 times in order not to leak information, because of if you just do it, say 5 times or 2 times. So the problem is that you kind of like leak where the piece might be, because of a queen, for example, here can get to like 8. A 9 in the center of the board can get to 1, 2, 3, 4, 5, 6, 7, 8 squares, but a 9 in the corner of the board can get to, let's say, just 1, 2 squares. So you don't want to give any information about where the piece might be. So you just send 8 requests, even though some of them might be empty. But because of your squares are encrypted, the other party is not going to know anything, essentially. So when you combine everything together, we have the state, which is exactly the state that we are looking for. So essentially, this solves the blockade issue. So the updated protocol is you make a move, you perform the refresh protocol. So A sends the location of their pieces to B, B sends the location of the pieces to A, and then we compute the intersection between the location of these pieces and the squares it can move to. So we do this from 0 to 7, that's just like 8 times, and 0 to 7, that's just 8 times. But then, so we can think of the zero knowledge proofs as a way to enforce good behavior. So when they do it the first time, they send a proof. Remember that this is a joint computation. So you cannot lie. Let's say you have seen a pawn that blockades you. You cannot lie that you haven't seen that pawn and then request for a square above, because of you have to send a proof that you are behaving correctly. So, and one of the rules of behavior, of good behavior, is that once you see a blockade, you do not ask for a pawn or a square outside that blockade. I don't know if that makes sense. So at the end of the day, you now have like a set of squares that you can capture your opponent's pieces on, and now you need to request for those pieces from your opponent. The problem with this is that if you just ask your opponent to give me pieces on A4, E4, E5, then your opponent essentially knows what you can attack, and that is not like dark chess. So the way we achieve this is with homomorphic multiplication. So essentially, we represent the squares that we care about as ones, and the squares we don't care about as 0. And then this allows us to be the query, but we encrypt this query. So this is the homomorphic element while keeping the linear structure. Then our opponent has a corresponding array for all the pieces, and they just do an homomorphic multiplication on your query. And so they have like a new set, which they don't understand what it means. But then when they send it over to you, you use your private key to decrypt that, and you essentially know what pieces you care about. So like 8 here and 9 here. And then you use zero knowledge proofs to also show that you are sending the correct encrypted query, which is basically the good behavior thing we talked about. So the progress, the UI is done, the PSI protocol is done, the chess engine in progress. So the problem was that the M1 proving time is really slow. So it took me like 10 minutes to prove on the M1. And then I got a Linux machine on the DigitalOcean, and I tested it on there. And it worked in like 100 plus seconds. And then because I didn't want to test so many times, I just started writing code for the chess engine. And I just wrote lots and lots of code because I thought it was going to work. And then when I got to a certain point, and I realized that, oh no, I am not writing this in the correct way, even though my local tests were passing, but they were not passing in the context of the smart contract. So basically, I wrote a lot of code that I had to change. And even though I knew what I had to do, I found it hard to implement it in Snarky because of you can't really, the branch, like my code had a lot of branching based on states derived from witness data. And currently that's not allowed, which makes sense because the circuits you generate during proving or compilation should be the same during proving. So I started looking at things like branchless programming. That didn't really take me anywhere. But then I basically ran out of time, and so I couldn't complete the chess engine. So I don't have like a proper demo, which is sad to show. But I will show the pieces that I made, and then I will continue learning more about Snacky and try and get the chess engine implemented as next steps. So feedback. I really want more logically complex examples. So I noticed that most of the examples were not when relative to the chess engine, for example, most of the examples were not that complex. And so I couldn't see an example where like a computation with a lot of branching parts would be implemented. And so it's made it really difficult to like look at something and then know that, oh yeah, this is how I'm supposed to do it. And Gregor was a lot of help. I asked him a lot of questions, and I got clarity, but then I just ran out of time, basically. And then stricter tooling that enforces good behavior. So if there was something that could have told me earlier on that, no, you're doing this wrong, stop. Yeah, I would have preferred something like that. Well, that is just my little feedback. So let me show the pieces that I have currently. So
also, sorry, you just have a minute left or a minute, 2 minutes. Is that in time?
I should be able to.
Great.
Yeah, I should be able to do it. So
awesome.
I have a chess UI, which basically has the fog of war elements in it. I basically forked a chess UI, and then I created a new FEN string format that essentially allows it to hide squares. So for example, once you put a 9, it means that you want a hidden square, and then the number of hidden squares that you want. So 9, 8 means like I want like 8 hidden squares. And so this is basically the FEN format. And then you can essentially use this to change the state of the board. And then the chess engine already generates an FEN string based on its state. So it could be plugged, but then this chess engine isn't properly doing state transitions. So it's almost useless, essentially. The PSI is here. So I was able to complete this. And I'm just going to go to the test because I don't have time. So you have a set, for example, and this has 5, 6, 4. So this is a private set for part A. And you have a set B, which is 4, 5, 7, which is private set for part B. So what's common is basically just 4 and 5. And what's common here is 5 and 4. So that's the intersection. So we create a PSI instance for both of them. They generate their own private keys. They encrypt their sets. And then basically we perform the intersection. And here we can return two things. We either return the intersecting index or the actual values. So the intersecting index should be 0 or 1. So I guess this is for 2, 0. So 4. So 0, 1, 2. So that's 4. And 0, that's 5. So from A's perspective, intersecting index are 5 and 4. And then the values are essentially 4 and 5. So this works, and you essentially run the test, which I did here. It passes. So the chess engine is here, but then I couldn't finish it. Basically, this code doesn't run in circuit, and it's quite painful. So I guess that's the end of my demo. If there are any questions, now is the time. Yeah,
Gregor.
I just wanted to say this is really cool. I don't have any specific question, but there are so many problems to solve, and wow, yeah, I think you got really, really far because it was a really hard problem, and yeah, it's interesting, and it would be cool to continue this and
yeah,
make it fully work. I'm happy to help with that.
Yeah, thanks.
Very, very nice.